Okay, everything's working. Good afternoon, everyone. I'm super happy to be here in Taiwan. And I also want to thank the organizers for allowing me to give this presentation, which is joint work with Peter Brown. We are both located in Telecom Paris. So as the title suggests, we provide a security proof for quantum key distribution that achieves two nice properties. The first, the property of optimality, and the second one, a property of generality. And before explaining a bit more about what are the ideas behind this proof, I want to explain why these properties are important, important properties for a security proof. So when we talk about efficiency, we must think about key rate instead of amount of keys, the length of the key that was produced per use of the channel. And usually the key rate, the function of the key rate as a function of the number of exchange messages by Alice Bulb, called the block size, usually takes the following form. We have some asymptotic key rates that we know that we can achieve in the limit of an infinite number of messages that are exchanged. But then there will be some finite size corrections, usually going as 1 over square root of n, that will decrease the key rate. And of course, for a given block size, you want to get as much key rate as possible. But by moving the curve up, we see that we're also moving it to the left. In particular, we see that by increasing the finite size corrections, the minimal block size at which you start getting a positive key will be smaller. And this is actually very important for practical applications. For example, satellite quantum key distribution or QKD in the networks, which are applications where typically we want smaller block sizes. But even in general, it's known that this, even for general QKD protocols, we know that there's actually a lot of pre-processing that must be done in a QKD protocol. And by going to protocols with smaller block size, we can simplify the post-processing and thereby making devices that are cheaper, smaller, and can run at a higher repetition rate. So to understand why we want a general security proof, we must go back to the history of QKD. That has been thought of as going from very structured protocols to protocols with less structure. So the initial security proofs of QKD tend to focus on these very simplified QKD protocols, the ones that we learn at school, BB84, concussion modulated CVQKD. But we quickly realized that if we want to prove the security of realistic hardware, we must take into account all the differences that exist between our idealized models and the real device, because the differences are important for security. So the follow-up research tend to start from these realistic implementations and then reduce the security back to the original very symmetrical protocol. The disadvantage is that while this security proofs for the simplified protocols, elementary protocols, tend to be tight, this reduction can lead to inefficiencies. Moreover, this reduction needs to be done on a case-by-case, case-by-case. And for example, my previous postdoc supervisor used to summarize this approach as saying, one protocol equals one PhD. So what we are interested here is try to prove security directly for a completely generic protocol. So this could be called a protocol-independent approach, or maybe a modern approach to highlight the fact that we start from different starting point, where we acknowledge from the beginning that our devices are not going to be represented by these idealized models, qubit model, etc. So actually, the ideas behind the modern approach, or the protocol-independent approach, go back to two important works. So first is a set of works centered around Renato Renners and his co-authors, who proved a general method to prove security for arbitrary QKD protocol, and they showed how the asymptotic key rate can be achieved in the limit of infinite block size. The problem with this method is that they didn't say how to actually compute these quantities, and this is where the second ingredient comes in. This is called numerical QKD, where the idea is to use ideas from convex optimizations to compute this key rate for different protocols. So if we combine these two methods, we have a method to compute tight asymptotic key rates for arbitrary protocols. The problem is that these methods are limited at the finite size level, making them not applicable in real-life situations. And especially when you compare this to the usual approach, that is maybe not as general, but at least provides security for reasonable block sizes. So the question is, can we try to solve these limitations of the modern approach so that you can finally use it in practice? So after this, a series of extensions called entropy accumulation or generalized entropy accumulation, for example, the last one was presented at QIP last year. They improve things on the finite size level, but the problem is that they introduce new limitations in the protocols. For example, for the generalized EAT, on my next slide will explain a bit more about this limitation. So the main idea of the starting point of this project was to think, okay, what if we use these two ingredients that were used, one ideas from information theory and one from optimization theory. Instead of having these tools used separately, what if we combine both? And by doing this, we're able to solve this problem and finally have a security proof for QKD that can compete with the usual protocol-dependent approach. So what was this limitation of generalized EAT? Well, actually, in this previous security proof, because of technical assumptions related to the fact that you need a sequential procedure, you need to limit the repetition rate of the protocol, where you need to wait for the pulse to arrive at both sides before you can send the next one. And we see that for some simple elementary assumptions, you're limited to a key rate of about 2 bits per key per second. On the contrary, in this method, we completely remove this limitation, so we can send all the pulses in parallel or quickly one after the other, which for the same assumptions lead to improvement of 6 orders of magnitude. Okay, so now let me tell you a bit more about the ideas behind this work. And if we want to have a method that is both general and effective, we need the right level of abstraction. Because if you look at typical QKD protocols, they tend to be quite complicated. You have some model, you have some device model that maybe can send some family of states, maybe mixed states. There will be some measurement that is performed, the POVM, then there will be classical preprocessing. So what we do is let's say, like, instead of considering this very complicated description of the device, we consider a more abstract model that we call the abstract protocol model, where we say that actually this whole protocol can be summarized by a single map that produces 3 key variables. The variables are the row key of Alice, the public announcements that were made, the test information, and then, of course, Eve's quantum memory. If you don't believe me that the whole security can be reduced to these 4 quantities, well, then consider the following security proof, sketch of security proof. We want to lower bound the randomness in the row key, conditioned on the information available to Eve, her quantum memory, and the public announcements that were revealed later on. And we want to condition this bound on a test on Z. So it means that all the quantities we need are available in this map. So what you then have is a more abstract method that would apply where we assume that we have a protocol described by some protocol map that satisfies certain of elementary assumptions, such as the fact that the map is trusted, that the map applies in tensor product, finite dimensions, and also that test information is public, which is always the case in QKD protocols. Okay, then our second idea, maybe it's a bit more technical, has to do with the way the final key rate will depend on the observed statistics. So what you have on the left is the amount of the key rate produced by the protocol. And here we have the different variables that are used to estimate the noise on the channel. For example, in BB84, this would be the bit error and the phase error, basically the errors observed when Alice and Bob measure in Z basis or the X basis. And we know these quantities needs to be estimated by the users. So while in blue, we have the, let's say, optimal asymptotic key rates we can hope to achieve for certain observed statistics. In real life, for most of the protocols, they're going to adapt this kind of non-adaptive, will have this non-adaptive property, where we see that the key rate will be either 0, and then once you are in some regions, you will get a fixed amount of key. The problem is that this acceptance region has to be chosen in a way that is conservative, and because of this, this will lead to reduction in the key rate by the order of 1 over square root of n, which is actually the level where we want to have a protocol that is tight. So what we do instead is that we have an adaptive protocol where we assume that we have a linear lower bound on the asymptotic key rate that we call a trader function. And in our protocol, the users need to estimate this trader function, which will then tell them how much key they have. So this is for the asymptotic security. But if you want to prove the security at a finite size level, there are two kind of statistical fluctuation that we must consider. The first one has to do with parameter estimation. Basically, the idea is to build confidence intervals for different parameters. And the second one has to do with privacy amplification. Usually in security proofs, these two fluctuations are considered independently in different steps of the protocol. But if you want to have a protocol that is tight, you must really consider the two things at the same time. So that's what we do with a new entropic quantity that we call weighted Renyi entropies, where basically we mix terms that use the trader function. For example, this is the exponential. So this information contains, for example, exponential. When you expand the exponential, you have information about the expectation value of the trader function, but also its variance in higher order moments, which are used to build confidence intervals. And then you have these Renyi terms that have to do with controlling the fluctuations in privacy amplification. Okay, so now we have everything ready for our security proof that will actually only require 2 steps. So with the formalism that I explained, what you have to do is that you have this protocol that applies in tensor product on different rounds. And because you want to consider security with information theoretic security, we must consider the worst case attack that could happen over a protocol. So here we have so in general, if is going to prepare an n-round state that could be arbitrarily correlated and even entangled across different rounds, which is called coherent attacks. So to solve this problem, we prove that if in fact you're looking for the state that minimizes this new F-weighted Renyi entropy, then you can actually prove that without loss of generality, the optimal attack is going to have this tensor product form, where each copy is identical. So now we are looking for the worst case attack over a protocol. We're able to reduce the security from looking for n-round attacks to single round attacks. But now we must find the worst case attack on a single round. And this is where the idea of convex optimization comes in. In numerical QKD, basically the framework that is used to compute asymptotic key rates using numerical methods, the idea is that you start from some optimization problem where you want to compute some entropy conditioned on some statistics. And the main idea is that while this initial problem is not convex, you can do a clever change of variables where you can make your problem convex. If you have a convex optimization problem, where basically you're minimizing a convex function over a convex set, when you have such a problem, you have many nice properties. For example, if you want to solve it analytically, you know that a local minimum is going to be a global minimum, but also numerically, we know that there exist efficient tools, efficient solvers to solve this kind of optimization problems. What we did was that if you now look at a different problem where you want to find the worst case F-weighted Renyi entropy conditioned on some linear constraints, then actually you can use the same change of variables. And in fact, this reduction will work each time you have an entropic quantity that is strongly subadditive. And so now, we're looking for the general worst case attack of n rounds, reduced to a single round. And then at the last step, we use a convex optimization solver to find this worst case attack. If we put everything together, we now have a method to obtain key rates for realistic or arbitrary QKD protocols. For example, this is an application for BB84. And actually, we also have methods to obtain finite size upper bounds. And we see that the lower bound, the security proof and the upper bound agree at the asymptotic level and also at the leading finite size order. So as a conclusion, I want to mention possible future extensions of this work. So the first one is to lift this constraint of finite dimensions and generalize it to infinite dimensions, which is possible because in all the steps in our proof, we never directly rely on the dimension. Dimension D never appears explicitly in our formulas. And this should be important, for example, to apply our security proof to discrete modulated CVQKD. Another one is to develop collaborations with experimental groups. In particular, I'm interested in developing a software toolbox to help experimental groups apply these techniques. And then finally, maybe more relevant for this audience, I'm interested in generalizing this IID reduction that we proved for QKD to more general scenarios. For example, QKD, this could be used to develop time adaptive protocols for satellite QKD, but could also find other applications in information theory. To conclude, maybe you're wondering, well, Tom, you presented this paper last summer in QCrypt. Where is it? Actually, it's almost ready. I just asked my son if he could proofread the appendix, and I'm still waiting for his input. Thank you.
Hey, questions for Thomas?
So it's a very interesting talk. I like it. But I have some questions.
Yes.
For the, I'm trying to understand the assumptions, right? You assume you're using the numerical framework, so you assume that we know exactly what state is being prepared by Alice. I mean, trying to see what.
Yeah. So we assume that the source of Alice is going to prepare some states, family of states that could be mixed states, but these states are completely characterized. For example, we know all the matrix elements of this density matrix. Is that the question you're?
Yeah, that's one question. So in an actual experiment, right, we don't know, right? So how do you apply this result to an actual experiment?
Are you referring to some kind of semi-device independent model where you have?
No. So in general, right, so the preparation will never be perfect, right? So someone is doing some experiment. So I have a best graduate student in the world, but she can never prepare perfect state. She doesn't know what state she's preparing, right? So how do you apply this result?
Okay. Yeah. So this security proof assumes that you have characterized your device. Maybe a possible solution to this would be proof on kind of continuity results, where we know that if you are epsilon close, if your protocol map is epsilon close to the protocol map you consider, then your key rate must be related by, but also be close. This could be a possible solution to this problem. Yes.
Hi, thanks for the talk. Looking forward to the paper. Just wanted to ask, why does this not apply to device-independent protocols? Like, what's the shortcomings of the proof for device-independent?
Okay, so it's because of the assumptions that we make. Basically, we are assuming that okay, the maps are trusted, but you could imagine lifting this assumption when you in the numerical optimization part. But the other assumption that you have is that these maps are in tensor product, which means that if Bob's detector measures a system and then measures a second system, well, second system, this measurement is going to be independent of what was observed at the first round. However, it seems possible that the methods that we have developed here could be generalized to more general models where you don't have this tensor product structure, but maybe some a more general causal model where you can assume, where you can have some influence from the past to the future. For example, basically the main step would be to generalize the IID reduction, which is actually the assumptions that you have behind this IID reduction make it not basically the assumptions that we have and the EAT model, which can be used for device-independent protocols. Basically, they apply in like non-overlapping sets. There are regions where they are comparable, entanglement-based QKD, but then you have protocols that are covered by our security proof, and then other protocols that are covered by the entropy accumulation. But since the methods that we use for the IIT reduction were inspired by the tools used in EAT, it seems plausible that we could generalize this IID reduction to also cover the cases covered by the entropy accumulation framework.
And a bit of a follow-up question. This weighted Renyi entropy that you have, do you expect that to also be able to be, do you expect there exists on chain rule to reduce it to the von Neumann entropy or something like this as well?
So most of the properties that you have for Renyi entropies will generalize to F-weighted Renyi entropies. And sometimes you use these tools. So for example, in our appendix, we use a book from Thomas Michel and show that most of the properties you have also follow are also true for these F-weighted entropies. Yes.
Awesome, thank you.
Thank you for the question.
Could you clarify a bit more about the linear adaptive protocol and fully adaptive protocol?
Yes, of course.
So what is the difference between the linear adaptive protocol and fully adaptive protocol?
Between orange and green? It's okay. So what you have on the x-axis is the different quantities you estimate during your protocol. Let's say BB84. They're going to look at the rounds where they use the same basis and look at the error. You have the bit error and the phase error. And assuming that we know them perfectly, we can compute the asymptotic key rate that goes along with it. So this will be the blue curve. However, that's not really how protocols work. Usually there will be, let's say, okay, we expect these statistics. And so we'll make a protocol that is optimized for these expected statistics. For example, some noise model on the channel. And this is going to be done by choosing an acceptance region, where if your statistics lie in this region, then you have some amount of key. And if they don't, then you have 0. So it's kind of all or nothing process. So what you have instead is, ideally we don't have a fully adaptive protocol. But we don't have this. We have a linearly adaptive one, where we kind of approximate this convex nonlinear function, gives a asymptotic key rate as a function of statistics, by a linear one. And since this function is differentiable convex, we can actually have this green curve match the blue curve very tightly in some region where we want to optimize the protocol. And we know this, because it's convex, this will always be a lower bound. Does this clarify?
Thank you.
Thank you for the question.
Hi, could you show the slide again where you had this Renyi conditional entropy?
Yes.
Yes. So I missed, what is this F? You didn't specify, I guess.
Okay, so this F is our trade-off function. Is the function that will tell us how much key we have. So this trade-off function will be a function of the Z variable, the statistics. But since our Z variable, since you assume all this information is public, we can assume that the statistics that we use are the public information. So we have a function F that is depends on P, public variable. And so this is for a classical quantum state, where K will be the key. We want to show that how much key do we have conditioned on P and E, and where in addition, and where we want to base this lower bound. So if you take F to be a constant function, then this will be the usual Renyi entropy minus F. And so you see that F can be seen as a kind of lower bound on the Renyi entropy. For example, if you say that, okay, what you have in the proof is that you assume that you must construct a trade-off function F such that this quantity is bounded from below by 0. And for example, in a particular case where F is constant, you will see that F will be a lower bound on your Renyi entropy. But here, in addition, we allow F to depend on P. And we show how to prove a composable security for an adaptive protocol just by using a lower bound on this rated Renyi entropy.
Okay, thank you.
Thank you.
Thank you for great talk. So I have a question for you. So how do you think the possibility of the SIB QKD? Last conclusion
The
slide.
conclusion slide, okay.
Yeah. So
Yes.
application to decreasing modulated SIB QKD. How do you think of the future and the possibility of SIB QKD?
The future of QKD?
Yeah. So
what do you
your
mean
opinion,
exactly?
Your opinion.
CVQKD. Okay, thank you for the question. Okay, so yeah, indeed, an important possible application of this work is CVQKD, and in particular, discrete modulated CVQKD, which is considered to be more easily implemented. And indeed, this work would apply to this to CVQKD, except for the assumption that we have finite dimensions. But actually, this is something that is very reasonable to lift, has been done previously, because if you have some bound on the energy, you know that the probability of having more than n photons is going to be low. So this part seems reasonable. And once you have done this, we could apply this security proof to discrete modulated CVQKD, where indeed, for the moment, there's not an efficient security proofs against coherent attacks.
Okay, thank you.
Thank you.
With that, let's thank Thomas and all the speakers of the session one more time.